But of course, this is calculus, and I want to be able to do cool calculus stuff with these. So I want to be able to say, okay, well, let's talk about derivatives. And here's where we actually come back and talk about derivatives for one last time. We have what's called first-order partial derivatives and second-order partial derivatives. So here we have first-order partial derivatives. And actually here I have a little bit of a typo. I don't think I had the right variable available for me. Most of the time we'll see first-order partial derivatives written like this. So here we'll have, say, f of x comma y be some function of both x, y. So it would be, 2x squared minus 3xy plus y minus 1. Perhaps it looks something like that. But what's important that it's a function of both x and y. Most of the time we'll see this notation right here, f sub x of xy. And this represents the partial derivative with respect to x. The other way that I could write that, you may see this in the homework, you may see this notation, rather than we're used to seeing dx over dy, or perhaps we might see dy over dx, excuse me, that's kind of what we're more used to seeing. So we might see in this case df over dx. Since we have these two variables already, we're used to saying like z is equal to a function of x, y. And what we want to do for partial derivatives here is we're not going to use the letter d. Instead, we're going to use the Greek letter del. So del z, del x. So this says the derivative of z, or excuse me, the partial derivative of z with respect to x. So you may see this notation pop up in the homework. I'm going to stick to this notation as much as possible, but just so you're aware, you may see this pop up from time to time. And then similarly for the partial derivative with respect to y, again, we're going to see f sub y of x comma y more often, but you may also see this as del z del y of f sub y of x comma y. So let's talk about partial derivatives because these are a little bit tricky. But once you get the hang of them, I think they're actually, they should be mostly review. It's just kind of an initial learning curve that we're going to have. So here, z equals f of x. Oops, again, I have a mistake here. This is f of x comma y is equal to 2x squared minus 3x squared y cubed plus 5y plus 1. So here I want the first order partial derivative with respect to x. So what that means is I want to, and I'm going to write this over here, find the derivative with respect to x. And another thing that this means, and this is I think the trickier part right here, we're going to treat y as a constant. So let's just rewrite our function right here. So f of x comma y, this is equal to 2x squared minus 3x squared y cubed plus 5y plus 1. So I want to keep this stuff right here in mind. We're finding the derivative with respect to x, and we're treating y as a constant. So it's going to follow all of the same derivative rules that constants do. So when I go to take the derivative f sub x comma y, if you have a term that only has an x, so first I have 2x squared, you're going to take the derivative of that exactly like we normally would. So the derivative of 2x squared, that is simply 4x. Then you might run into some terms that have both x and y. And what I'm going to do here is I'm going to say, for the purposes of this problem, notice we're taking the partial with respect to x. I'm going to cover up y for a second. Just pretend it's not even there. Just pretend that's not even there. Cover it up on your paper. say, okay, I want the derivative of negative 3x squared. Well, the derivative of negative 3x squared, that's going to be negative 6x. But that y is still there. If you look at the derivative rules for constant multiples, it means we just multiply the derivative by that constant. So we're going to multiply our derivative, which is 6x, by this constant, which is y cubed. So really I have the derivative, which is right here, 6x times y cubed. This is just a constant multiple coming down into the first derivative with respect to x. Then I see this right here, a term that only has a y. So here's where this is going to come into play a little bit more. Hopefully this will be a little bit more easy to digest here. It says treat y as a constant. So that means 5, which is a constant, times y, which is a constant. This term right here, 5y, that is a constant. Well, I know that the derivative of any constant is 0. And 1, well, that's a constant. We're used to seeing that derivative of that is 0. You don't necessarily need to write in 0, but I like to do that here just so that it's very clear exactly what's going on. So my first order partial derivative, f sub x, of x comma y, is 4x minus 6xy cubed. Here is my first order partial derivative with respect to x. And then, of course, I can evaluate my first order partial derivative at a certain point. So here I would like to evaluate my first order partial derivative at 2 comma 3. So here f sub x of 2 comma 3. Hopefully we understand exactly what this means, but if not, we're just going to take 2, plug that in for x, 3, plug that in for y, and evaluate it. So here I have 4 times 2 minus 6 times 2 times 3 to the third. So this should be 8 minus, here 6 times 2, I should have 12, 3 to the third, that's 27. So let's see, 8 minus 12 times 27. I don't trust my arithmetic here on this one, 324. So let's see, I should have negative 316. All right. Now, I want to say, okay, well, here's the partial with respect to x. That's all well and good. Now, I would like to find the partial derivative with respect to y instead. So I'm going to go back to that original function. I'm going to go back to f of xy, which is 2x squared minus 3x squared y cubed plus 5y plus 1. So here in this case, we can kind of follow these same directions that we were looking at. We're just going to kind of switch around x and y. So we want derivative with respect to y. And this time we're going to treat x as a constant. So when I go to find the first order partial derivative with respect to y, so I want f sub y here, I'm going to look at this term right here, 2x squared. 2, that is a constant. X, which is a constant, being squared, that is a constant. I have a constant times a constant. So this whole term is a constant. Derivative of a constant is 0. So I'm just going to put that 0 there so I know exactly what's happening to that term. Derivative of that term is 0. Next, I move over here to negative 3x squared y cubed. Here I have this term that has both an x and a y term. So again, just like I did with the in the last example, I'm going to cover up my opposite variable. So I'm going to cover up this x here for a second. Pretend it's not there. So I really want to say, okay, well, I want the derivative of negative 3y to the third power. And I'm going to take the derivative of that like I normally would here. Well, that would be negative 9y squared. But the constant, because we're multiplying by that constant, the derivative of that part isn't 0. We just multiply the derivative by that constant. So we're going to multiply the derivative by the constant, which in this case is x squared. So this x squared is just coming down into the next step. Same thing happened over here with this y cubed. Notice this y cubed just came down into the next step. All right, so we have our first few terms, plus next up I've got a term that only has a y. This should be a little bit more manageable. Derivative of 5y, that's just plus 5. And then the derivative of 1, well, that's just 0 since it's a constant. So my first order partial derivative with respect to y is negative 9x squared y squared plus 5. Here is the first order partial derivative with respect to y. Notice that the first order partial derivative with respect is different, the first order partial derivative with respect to x is different than the first order partial derivative with respect to y. So you will not get the same thing if you take the partial derivative with respect to x and the partial derivative with respect to y. We should have two separate derivatives. And then, of course, I may want to evaluate that at a certain point. So, okay, we're going to go ahead and take our partial with respect to y. And actually, let's change our color up here. Let's do this in black. So I want to take 4, plug that in for x, 1, plug that in for y. So here I have negative 9 times 4 squared times y is 1 squared plus 5. So I have negative 9 times 16 plus 5 here. So 9 times 16, that gives me minus 144 plus 5. Here I'd have negative 139. So I think this is the tricky part right here. It is to treat that opposite variable as a constant, treating that variable that you're not thinking about here. So if I'm taking the partial with respect to y, treating x as a constant. This is probably the most difficult part of this section, but once you have it down, we're using all of the same derivative rules that we've been using. So we're still going to be using the power rule most of the time. We may still need, on occasion, the other derivative rules. So in the next video, we're actually going to see what does it look like if we need a chain rule. Then we're also going to say, okay, what happens if we want, say, a second derivative? What does that look like? So take a look at our next video, which is, unfortunately, it's our last video.